Okay, let's get started. Can you see my screen?
Yes, we can.
Okay. Uh, so today we will be discussing single phase AC and special purpose motors. So far we discussed the three phase system and three phase induction motor, three phase synchronous motor, three phase synchronous generator, and then DC motor, DC generator. But then from now on, we will be looking all single phase AC motors. And then, at our home, mostly all of the loads are the single phase system. And there are special purpose motors. For example, what is the motor that is used in computer? What is the motor that is used in printer or digital clock or elevator? So you see hair dryer, lawnmower. So in that way there are toothbrush. In that way there are lots of various special purpose motors. And as you can guess, all those are very small sized motor. So sometimes instead of single phase AC or special purpose motors, those are called the fractional horsepower motor. Fractional horsepower. Because you know that 1 horsepower, 746 watt. And then in most cases, the rating of these motors are below 1 horsepower, like below 746 watt. Accordingly, they are called fractional horsepower motors. Therefore, currently the book that I am following, the chapter title, chapter 9 currently I am, this is the title. But if you see other book, sometimes the chapter title just fractional horsepower motor. So we will be looking those. Now, you see here is just some list that single phase AC motors can be two types. One group can be single phase induction motor, and then the other group can be single phase synchronous motor. I mean, beyond these two classifications, there are other various motors as well, but these are the main thing that we'll be discussing in this class. So you see, we have learned three. You see, pretty interesting as you can see that first we have covered three-phase induction motor, and now we are covering the single-phase induction motor. Shouldn't be the reverse thing that first we should cover single-phase induction and then later we should go three-phase induction motor. But you will notice, I mean, today I will be discussing that single phase induction motor is somewhat complicated in theory, in operation, than the three phase induction motor. That is the reason, I mean, not only this book, any electric machine book, always three phase induction motors is covered first and then the single phase. Today you will notice soon that this is a little bit complicated than that. And then one of the best example of the single phase induction motor that you can see at your home, which is the ceiling fan. So each of you have at your home the ceiling fan. The ceiling fan is the example of single phase induction motor. That's why, I mean, as a engineer, so instead of telling ceiling fan, so you might say the engineering term, this is single phase induction motor. Okay, and then there are lots of classification. Split phase motor, capacitor restart motor, capacitor run motor, and capacitor restart capacitor run motor, shaded pole motor, linear induction motor. And then among the group of single phase synchronous motor, hysteresis motor, reluctance motor, stepper motor, subsynchronous motor, and then the one that is used in computer, it is called the servo motor, and there are other types. And then there is other thing, universal motor. So probably in the machine lab, you might have noticed that we have that Hamden big table. It is written the universal machine. So that is that universal motor. So universal motor means the same motor can work on both AC and DC. I mean, it's quite interesting. I mean, today I will be discussing. Accordingly, it is called universal motor. I mean, so far we discussed that AC and DC, we distinguished. But then universal motor means it can run on both AC and DC. And then there is permanent magnet DC motor. Similarly, there can be permanent magnet synchronous motor. So meaning that we don't need any excitation. It is not like sun type or series type or compound type or any other type. The magnet is fixed. Magnet is permanent means in this case maybe 25 years or 30 years, very long time. So you don't need to change anything. Accordingly, it is called permanent magnet. So therefore, in terms of excitation, you don't need to do anything. Even in case of synchronous motor, synchronous generator, we discussed under excitation, normal excitation, over excitation, and leading lagging unity power factor. So you don't need to anything. You can eliminate everything because magnet is permanent. So therefore, in this class, we will be discussing that permanent magnet DC motor. Therefore, gradually, let's get started. First, let's look at single phase induction motor. Now, let's take you to the board for a minute, and then you will understand. Hold on. So everybody, see, let me write on that. So we are discussing uh, the single phase induction motor. That thing we are looking. So now, for example, this is that rotor body, and this is that stator body. To the rotor body. So one thing is that in most of the single phase induction motors, as I told that those are called the fractional horsepower motor, rating is very low. Therefore, for the rotor circuit, it is most cases squirrel cage type. Squirrel cage type means they don't have any winding, they just have conducting bars. So therefore, everybody assume that this rotor to which the shaft is connected, it is squirrel cage type. So we are fully fine. So this is the stator. On the stator, because this is single phase, there is only one phase of the coil. It is not like three-phase induction motor, then there is B phase, C phase, only one phase. And then you are applying the voltage here. This is the terminal voltage, and then the current is flowing. This is only one phase, so even I am not designating by I. So what will happen? There will be a flux. But what will happen that this flux is not rotating flux. You remember when we discussed the three-phase induction motor, then we have another coil here, and then we have another coil here, another set. This is, sorry, C phase, B phase, and this was A phase. And then once you applied the three-phase voltage to the three sets of coil, and then there was a rotating magnetic field. So we say, okay, this is the, and that is rotating at synchronous speed. But in this case, because this is only the single phase, we don't have the other, sorry, we don't have the other coils. So let me try. We just have only one set of coil. So what will happen? The flux will be built up, but it will not be revolving flux. It is not. It is just pulsating because we are applying the AC. Of course, this is the AC. We are applying the AC. So the flux that is being produced, that is alternating in nature, that is pulsating with time, but stationary in space. With respect to movement, it is stationary. So that's why what will happen, because this will just oscillate, this will just pulsate here, this plug, it cannot produce any voltage on the rotor circuit. The rotor are squirrel cage type, it has conducting bar. Therefore, if there would be a revolving field, then there must be voltage built up on the rotor circuit. But in this case, flux is just being developed, but it is confined here. It is just pulsating, it is just oscillating only here. It is not rotating. Consequently, there is no voltage buildup. Then there is no current and no flux on the rotor circuit. So for example, let me say that this fire is zero. Rotor flux is zero. This is only the stator flux. Consequently, there is no interaction of flux, and hence there will not be any torque. Torque is zero, and consequently, the shaft is not rotating. So, meaning that conclusion is that single phase induction motor is not self-starting. It cannot start. So, because of the nature of the flux. So, therefore, everybody, could you follow me so far?
So far, yes.
Yes, yes. So just keep in mind that conclusion single phase induction motor is not self-starting. So then that's the question. Like few minutes back, I told you that ceiling fan is the single phase induction motor. Then how does the ceiling fan move? So you see the interesting question. So that I will be addressing you, and that will be discussing extensively today. Those things, that how does, then easily you can guess, we need some alternative arrangement. We need something to do. Only one coil is not enough because it does not have any, it is not revolving. To produce the voltage, you need the relative motion. So therefore, this is just changing, but it is confined here. It is stationary in space, pulsating in nature, pulsating with time, but stationary in nature. There is no movement. And then, of course, this is the motor. So you cannot connect a prime mover to rotate it from the beginning. Then it will not be a motor. So motor should get rotation with the help of electrical power. So then what is the thing, why it is not moving and why the starting torque is zero? The thing is that initially you need to gear it up. At the beginning, the main thing is that the internal thing is that the initial starting torque is zero. That is the thing. So this means that something is happening. So in fact, what happens, that although I said that there is no rotating magnetic field, but essentially there is two magnetic field. One is rotating in this direction and other magnetic field is rotating in this direction, and they are cancelling each other. Consequently, the resultant torque is zero. Like if you say that this one is clockwise plus, anti-clockwise minus, or if you say this is plus and this side is minus, and they are cancelling each other. So this means that there is forward rotating field and there is backward rotating field. That forward and backward rotating field is causing the resultant torque zero. So therefore, let me draw on curve. Hold on, just a moment. So what happens? This axis is the torque, and in this axis is speed. I'm just trying to make you understand that why the starting torque is zero, why it does not move. We understand that because there is no rotating field, but actually there is rotating field, but two. This is our zero position. So actually this thing happened. You see, okay, hold on. Wait. Clean up this up. I'm trying to draw the, sorry, and then, okay, so and then this means this is on curve, what I am doing. So this is on curve, on type of curve. And then there is on the negative side, there is another curve. This side is plus, this side is the negative side. And this axis is the speed. So now everybody say, I can make a resultant. Yes. So this is due to the forward field. Let's say, let me label. This is due to forward field, forward rotating field. This one is due to backward field. And then this line, that is the resultant. Resultant. So this means that in case of single phase induction motor, once you apply the AC voltage to the single phase coil, then there are two magnetic field, two rotating magnetic field is produced. One moves clockwise, other moves anti-clockwise. So if you say that clockwise rotation is forward field, or if you say the anti-clockwise is forward field, then the other one is backward field. And you see, if you remember the induction motor characteristics curve, torque versus speed, if you just remember the three-phase system, this was the type of this point is called the pull-out torque or the maximum torque. So therefore, one curve is going in that way and other curve is in the bottom, reverse direction. And then I am point to point, I am connecting, you see. The sum of this point is here, the sum of, therefore at this point, I mean, I just drew by hand. It does not look equal, but it will be equal, you see. Meaning that the resultant curve at the 0 point, torque value is 0. That is the meaning that its starting torque is 0 at the 0 time. So that is the reason, that's why a single phase induction motor is not self-starting, because it produces two magnetic field. One rotates in the forward direction, other rotates in the backward direction, and they cancel each other. Consequently, at the starting point, torque is 0. Now, how to start? At the beginning, you have to provide some torque. You have to create such a situation so that at the beginning, for example, you have some torque. Yes, you see, from the 0 to here, maybe 100 Newton meter, 200 Newton meter, something you have to produce even at the 0 moment. That's the thing, that's the key. That we will be doing now. Everybody, could you follow me so far?
Yeah, makes sense.
Okay. Then now let me take you to that slide again, and then I am coming here. So everybody see, that is the thing I wrote now. Single phase induction motor is not self-starting. Since the single phase AC voltage supply to the stator winding produces non-rotating, which is stationary in position and pulsating with time magnetic field. And then, as I explained, that according to double revolving field theory. So therefore, this double revolving field theory, this is applicable to single phase motor only. This is not for the three phase. In three phase, there is only one rotating field. Either it is rotating in forward direction or only in backward direction. So therefore, I mean, you might be asked this question that what is the double revolving field theory? Then you should answer that this is related to the single phase induction motor. And what is the theory? According to the theory, the stator pulsating magnetomotive force wave can be decomposed into two magnetic fields. One is forward revolving field and the other one is backward revolving field. The thing that just I explained. So therefore, if you see this one, I mean the curve that I was showing, everybody look, this is the that picture that I was explaining you. If you see the book, this is figure number 9.2, torque speed characteristic. So everybody see, I am plotting torque versus speed. So this is the curve, it is going. So you are familiar this pattern. This is the torque speed curve of three-phase induction motor. The same thing is happening, and I can say this is the torque due to forward field. And then there is the other thing which is rotating just opposite to this one. And then you see I am connecting point to point. I am summing up. Therefore, this is the 0 position. At the 0 position, the torque value is 0. Just now I explained. This is the resultant curve. So therefore, in the exam or any time, if you are asked to draw the uh, torque versus speed curve of single phase induction motor, then it is better to show all three. I mean, of course, if you just show this one, this bold on, that is fine. But you can show that, okay, this is the forward field, this is the backward field, and this is the resultant field. So the thing is that you keep in mind, it must start from the 0 point. Sometimes in some book for single phase induction motor, only this portion is shown. And you see it must start from 0 to indicate that it has starting torque 0. And that is the reason that it is called not self-starting. So, but we have to start it. So therefore, now this representation, mathematically we can represent this one. So therefore, everybody see what I have written, that for a sinusoidally distributed stator winding, the magnetomotive force along a position theta can be expressed as if theta ni cosine theta. So you all know here we are using the term MMF, magnetomotive force. So for the coil, magnetomotive force means multiplication of current and number of turns. Everybody note down the definition of the magnetomotive force of a coil. Number of turn multiply the current flowing through it. That is called the magnetomotive force, Ni. So that's why we are assuming that once we are applying the voltage on the stator winding, then it is gaining the magnetomotive force, which is this one, with respect to theta position. As I was telling you that it was just pulsating in space. So f theta ni cosine theta. So I have written down the meaning. Now you see the small I indicates the instantaneous value of current. Because we are discussing single phase induction motor, that single phase means this is the AC. Of course, this is AC. So that's why I is the instantaneous current. So therefore, how to represent the instantaneous current? You all know I equal to I max cosine of omega t. That I is the time function. Then now if you substitute this equation 2 in equation 1, then what you will be getting here? If a function of theta and t. Here it was like only theta, but this is time function. That's why I have written theta t. That in that I max cosine of omega t cosine theta. Then now here just you apply the trigonometry. Everybody from trigonometry, if there is 2 cosine of omega 2 cosine theta, then cosine of omega t plus theta, and then cosine of omega t minus theta. Like 2 cosine of A cosine of B, that formula. So, but there was no 2, that's why you see there is one half. So Ni max over 2, then cosine of omega t minus theta, and then the other is cosine of omega t plus theta. So this means that everybody see that if you plot cosine of omega t plus theta and cosine of omega t minus theta, if you consider, if you plot it with respect to 0 point, one has the plus angle plus theta and other has the minus angle, the reverse side. Therefore, if you say that, okay, this one is my forward field, FF, I have written forward rotating field, and then the definitely other one is the backward rotating field. Or if you say that this is forward field with respect to this one, this is the backward field. So therefore, this thing proves the fact that single phase induction motor has two types of magnetic field. One is called forward field, other is called backward field. And that forward field and backward field, that is causing the problem. It is not helping start the motor initially. We have to overcome that situation, because if this nature and this is generating inherently, you cannot avoid it, but you can put some control means to tackle this situation, to overcome this barrier. That we will be doing. And then now you see pretty interesting thing, because there are two types of field, forward field and backward field. Accordingly, you see I have written there are different slips for forward and backward rotating field. This means you all know that slip definition from the viewpoint of three-phase induction motor, synchronous speed minus rotary speed over synchronous speed, then taken as a percentage. That is the definition of slip. So therefore, that is applicable to forward rotating field. But then for the backward rotating field, the slip equation is different. I am showing you, it will be 2 minus the forward slip. Therefore, the slip definition that you have learned in case of three-phase induction motor, that equation is applicable to the forward rotating field only. For the backward field, it has different slip. Easily you can guess that because it is rotating in the backward direction, so therefore motor direction will be opposite. Consequently, slip equation will be different. So therefore, for a moment, I think I have not written down it here. It will be 2 minus that forward slip. Let me take you to the board and then you will write down that you will need to solve the problem. Hold on. Okay, so let me write down. So I will just write down this on the SF means forward slip, slip due to forward field. That is the meaning. So therefore, the standard equation. So the NS minus NR over NS. So therefore, you all note down that S subscript F. F refers to that forward field, meaning that this is slip due to forward field. So which is the same. Now, what will be the slip due to backward field? Let me write down here. Uh, Backward field due to backward reaction. So everybody see, this is synchronous speed. Then this was the rotor speed, right? So that due to backward field, rotor shaft will rotate in the reverse direction. So therefore, meaning that I will put on minus sign here. Therefore, NS minus. So this minus is just to see the difference, but this minus is coming due to backward field. Backward field will rotate the shaft on the reverse direction. That's why I put minus sign, and then this is NS. So now let me, we don't need this thing. Okay, so therefore everybody see here this one. So what you are getting? So my denominator is fine, but in the numerator it is getting plus. So therefore NS plus NR. And then now simply it can be expressed, everybody see, I can write like 2 minus, this is NS, the NS minus NR. Everybody look, is the meaning is the same, this one, NS plus NR over NS, that can be written 2 minus NS minus NR over NS. So you see, in the denominator it will be NS, and then 2NS, 2NS minus NS, so 1NS, and then plus, minus minus, then plus. So it is the same. And why I did that? I did that because, let me clean up this thing. I did that because, hold on, this is 2, and then everybody see that this portion, NS minus NR over NS, that is the standard definition of the slip that we have learned, which is the slip due to forward field. So you can write 2 minus SF. Just to express the, just to show the relationship with the forward slip, that's why I'm writing in that way. I mean, definitely, of course, this is correct. But then to show the relationship, how it is related to the forward slip, that's why I'm writing this. Therefore, everybody, you will be using to solve the problem, this one to calculate the slip due to forward field, and you will be using this one 2 minus SF to calculate the slip due to backward field. This means ultimately you just remember this one, that SB is 2 minus SF. Yes, you will be remembering this one. So everybody please note down this one, and then you already know this one. So SF and then SB 2 minus SF. Today we will be solving on numerical problem. That time you will be needing this equation. Everybody, do you get me? Could you follow me?
Yes, I do. But also, you were saying that the two minus that came from the SB equation.
Yeah, yes. You see, first you understand this one, right? Yeah, why I put the minus sign here.
Yes, because it's rotating in the opposite. Yes.
Opposite, and then this minus minus plus. And then I said that, okay, you can, you see all the, this is SB. I started SB equal. This means I am continuing the SB. So that's why I finally wrote this one. Of course, all the calculation is for the SB. So and then instead of living in that format, because if you live in that format, then you cannot tell that what is the relationship with the SF forward slip. That's why I'm trying to show that the forward slip definition is NS minus NR over NS. That's why I wrote, you see, this thing you can write in that way, 2 minus this one. So do you see that the meaning is the same? The value is the same, this line and
Yeah.
this line.
Now I can see. Yes.
Eh, can you see now? Yeah.
Yes,
Because
sir.
you say if you go back from here there, like what result you will be getting? You see, look this one, 2 minus this one. So ns minus nr over ns. So therefore, what will happen in the denominator? You will be getting ns. Just apply the algebra. So therefore, it will be 2ns minus ns. So 2ns minus ns, that will give you the ns, and then this minus minus, it will be plus nr. I mean,
Oh, yep. Okay, that makes sense.
everybody, do you understand this thing? I mean, what I am saying that I can write, I can express this on in this way. That it is the same thing. Just look the algebra. Just this is the just make this calculation. If you have this one, will you not get this one? So that and
Yeah, it makes sense.
yeah, yes, it is the simple algebra, simple thing. And then why I wrote in that way? Because you see that ns minus nr over ns, this one look as a forward slip. That is the definition of forward slip. So I can express this portion by SF. That I did. This therefore this two is this two, and then this portion is giving me that one. This portion is that forward slip. That's why I said 2 minus SF. And finally I just wrote here in box that SB is 2 minus SF. I think everybody now understands. Now, one thing that because of these things, because of the two slip and because its starting torque is 0, motor is not able to rotate, but we have to make it rotate. So how to rotate that? So therefore, again, let's see to that slide. So we understand this one. Then after that, everybody see what I have written. How to make the single phase rotate? To make the single phase induction motor rotate, auxiliary winding on the stator is needed. So therefore, definitely you can guess that some additional winding is needed. On winding is not enough. And that auxiliary winding is placed 90 degrees apart from the main winding. And then what happens? What does the auxiliary winding do? What is the role? The interaction between the main winding flux and auxiliary winding flux produces a revolving magnetic field, which in turn makes the rotor rotate. This means that there was only one winding. Even if you put another winding, then there will be another sets of flux on that auxiliary winding. Now there are two sets of flux. Just everybody simply take in that way. To produce any torque, to make any rotation, you must need two sets of flux. If there is only one, then there is no interaction. If there is two, then there is interaction. So of course, there is some design or the arrangement question about the main winding, auxiliary winding. I'm showing you the pictures on. There is difference between the main winding and auxiliary winding in terms of the resistance value. I mean, both are the coil, but one has higher resistance than the other. And why that I am explaining. But at least you see that because there is only one set of winding, that's why it was not able to produce torque. And theoretically, inherently, we look because of the presence of backward rotating field in addition to forward field. And now we have to create the interactive flux. Only one flux, only the main flux is not enough. That's why you need auxiliary flux. And then it will produce revolving field, and once it will produce revolving field, then rest of the thing is the same as to the three-phase induction motor that you have covered. what will happen? Then that revolving magnetic field will produce voltage on the rotor, squirrel cage rotor. And that rotor will produce another flux. And then finally, there will be interaction between the rotor flux and this revolving magnetic flux, which finally will make the rotor rotate. So therefore, just the thing is that initially you have to create this situation. And that is the reason if you now open the ceiling fan, if you see the stator circuit of your ceiling fan, you will definitely notice there are two sets of coil. One is main coil and other is auxiliary coil. And you will notice that in the auxiliary coil, not only an inductor, but also there is a capacitor. Maybe it may happen that some of you have already might have noticed inside the ceiling fan, main coil and then the other auxiliary coil plus a capacitor in series with the auxiliary coil. That capacitor is needed to improve the power factor for better operation, much noiseless operation. We are gradually coming this point. So now the question is, I said that there will be auxiliary winding and then how that work. Here I think so I have a picture for you. So everybody see now, I mean, don't concentrate on the rotor. Rotor, as I said, the rotor is the squirrel cage type. I mean, these are showing that, okay, the current is flowing and these are the conducting bars. The circles are representing. Concentrate on the stator circuit because that magnetic field will be producing on the stator circuit. Therefore, everybody, see, as I said, this is the stator circuit, outer side. It is just showing in terms of the circuit. This means that you are applying voltage, current is flowing, and then current is going to the main winding, and you see you have another auxiliary winding. So the current is some current is going to the auxiliary winding only. And what is happening with the auxiliary winding? Can you see there is a switch? It is called centrifugal switch. So meaning that it will not operate always. I mean, initially it is enclosed. Everybody see the switch is open here, but at the beginning switch will be closed so that the current can flow through the auxiliary winding. And once why it is open, once the rotor attains 75% of the synchronous speed, then this switch will be open. Meaning that you don't need the auxiliary winding, just main winding is enough. The thing is that again, like why we need auxiliary winding? Because initially its starting torque is zero. So rotor shaft, I mean shaft is not shown here. You keep in mind that there is the shaft. Initially the shaft is not rotating because starting torque is zero. You have to produce some, you have to kick it off at the beginning. That's why that oil auxiliary winding is needed. Once the rotor will start rotating, then it is gaining. Due to it inertia, automatically it will rotate because you are applying the voltage. That is enough. At the beginning, you just need to start it. So that's why that auxiliary winding is needed. So now everybody see, that is the thing I am showing. You see the here you see the it is called the split phase motor. I am coming that one. Everybody see this one. This axis torque and this axis that synchronous speed. And you see that I have written percentage 25, 50, 70, 100%. This means when it is 100%, this motor is rotating at full speed. Now everybody see we discussed this curve today. Thus the dot, it will start from zero. That is the nature of the single phase induction motor. And see, I have written main winding only. When you have only one winding, then this will be your curve. But once you have the both main and auxiliary winding, you see, starting torque got increased. Starting torque got increased. This is the percentage torque. So main and auxiliary winding the result. And then as I said, the switch was closed here and you will be noticing the speed. Gradually you see the torque is gaining, and then the speed is increasing. Once speed becomes, you see, 75% here, then the centrifugal switch operates, meaning that centrifugal switch will be open. And that's why you see after this point, like from here to here, main and auxiliary winding, and then you are taking it out, you are switching off. consequently it is falling, and then the main winding only. But by then there is enough speed, so it will not stop, it will continue to rotate. So the question is, this is the question, this point, that why in case of main winding it is starting from zero, and what did the auxiliary winding do that is making the torque become, for example, 150%. Well, what it is doing? So you see, the way I have shown, it looks like just a coil. Then what additional thing it is doing? Still it is single phase, it is not three phase. So how it is helping? Now if you see the vector diagram here, everybody see. So this is the total current, and this is the IM. IM refers to the main winding current, and IA refers to auxiliary winding current. Now if you see this vector diagram, that will help you to understand that how you get this amount. So everybody see, first I am drawing this VT, terminal voltage, this one. So you see it looks like car, because when I was scanning this one, it became, but everybody keep in mind, this is a straight line. And then, of course, you everybody understand, because these are the coil. So you all know that in case of, if it is pure coil, if it is pure inductance, then definitely current will be 90-degree lagging. So like you see, the current should be straightforward here, 90-degree. But everybody keep in mind that these coils have some resistance in it. There must be some resistance. These are not the pure coil. So now that is the reason, because there are some resistance. So therefore, of course, it will be lagging angle, but not pure 90-degree, because not pure inductor. That's why first here I, and then there is some angle, power factor angle, and then other one is the IM. And then this is showing that the resultant current, this on I, resultant of IA and IM, dot, 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 and this portion. So this is the resultant vector. Now, here there is one question. Can you everybody see? IA is plotted here, but then IM is plotted here. So IM was the main current and IA was the auxiliary winding current. But then why IM is not here and IA is not here? Everybody, do you understand what I am saying?
Yes.
So don't you think that what is it just the choice that you will be placing IM here? Why not putting the IM here and IA here? So of course, everybody understand that these are the coils. So both currents will be lagging, right? That is right, yeah. That current will be lagging. So therefore, with respect to voltage, both current are lagging. But then if you compare IA and IM, what is the relationship? There is alpha angle difference. You see, there is a difference between IA and IM angle, which is alpha. But then that is, I am asking that question, what's wrong if I place IM here and IA here? So therefore, it is not the choice. Therefore, definitely you can guess that this auxiliary winding has higher resistance than the main winding. That is the reason. So now everybody see, because it is the showing the relationship, this is the power factor angle between voltage and current. Definitely, because this is IA, it has higher resistance than this one. So if it has higher resistance than this one, this means that this is more lagging. As I said, if resistance is zero, for example, here if the resistance is zero, then this will be fully 90-degree lagging. Similarly, if its resistance is zero, it will be fully 90-degree. I mean, both will superimpose. Both will be on the same line. But what has been done, how to design this one? It has higher resistance than this one. So that's why, because it has higher resistance, that's why it is more leading than the IM. That is the difference. Because you all know cosine theta power factor is R over G, R over impedance. So therefore the coil that has higher resistance, that will have better power factor, improved power factor. That's why you see it has the lower angle than the IM. So now in real practice, now how to do that? Because by looking like it is coil, right? It just look coil because it is not showing, I am not showing any resistance here on here. Just by looking, I am explaining that thing. So that's why in real practice, what happens, main winding is thicker in shape than the auxiliary winding. So just a moment, let me take you to that board. Then it will be much more clear to you. Let me clean up these things. Now, let me draw two things. For example, this is on cable, and then this is another cable. This is thick. This is thick, and then this is thin wire or the thin cable. And then their distance, their length is the same. L is the same in both cases, whatever it is, 1 meter or 1 feet. So therefore, which cable has higher resistance, this one or this one? This is thick, its cross-sectional area is thicker than this one. This is thin, this is thick, but the length is the same. So which cable has the higher resistance, this one or this one?
Thick cable has a higher resistance.
Thick cable has the higher resistance. So is that right? So you see that it has the higher cross-sectional area. Cross-sectional area A, and then this is also a cross-sectional area. So I think, let me write down this one. Can you all remember this equation?
Oh, so I'm exactly wrong.
Yeah. The resistance equal to rho L over A. So rho is that?
Resistivity of the material.
Exactly. And then A is the cross-sectional area and L is the length. Yeah. So therefore, because you see that this is thicker, so it has the higher cross-sectional area, the thicker resistance, the thicker cable. So that's why you'll be getting lesser. So therefore, here R is small. Here R is small. And then the thinner cable has the higher resistance because of this equation, because it has low cross-sectional area. So that's why that we are discussing. For example, this is the main coil. So let me just discuss this. This is the main coil, and then this was our auxiliary coil. This is, sorry, auxiliary, and then this was the main coil, this coil. So because auxiliary coil will remain in the circuit only until that 75% of the synchronous speed we are discussing, you see. Then there was a centrifugal switch, and then we will disconnect it. We are discussing. We will take it out. So that's why it is thinner, because, and then the main winding is thicker because it will remain in the circuit forever, always. 24 hours it will work if you run the motor 24 hours. That's why the thicker the wire, then higher the withstanding capability of the current and the temperature. Therefore, if you compare these two cables, definitely thicker cable will carry higher current because it has the small resistance. And that is expected because main winding will remain in the circuit longer time. And then also we are noticing that thing that we are applying the voltage. Let me clean up this thing. So one more thing, and then everything will be clear to you. So it was the vector diagram. This was the terminal voltage, and this is the auxiliary winding. So the auxiliary winding was current like that. It was I, and then the main winding current was like that here, that we noticed because of this nature. And then there was an angle alpha. this angle. So therefore, what actually happens, that angle is important, that angle is needed. So therefore, what happens in a motor actually, in the torque is proportionate to that Ia and Im, and then their sine of alpha, sine alpha, sorry, sine alpha. This is the torque equation. Torque is proportionate to I, auxiliary winding current, multiplied by the magnitude of main winding current, and then their sine of alpha. So now if I omit that proportionality, so let me write down it here. Therefore, torque is K on torque constant, that Ia, then Im, and the sine alpha. So everybody, you can write down this equation, that torque equal to K Ia Im sine alpha. This is in Newton meter. This will be in Newton meter. The amount of torque in a single phase induction motor. Now everybody see, because there is sine alpha, so if alpha is 0 degree, then what is your torque value? Torque is 0. On the other hand, when alpha is 90 degree, then torque is the maximum. So therefore, at least come back that there must be some value of alpha. Because if alpha would be 0, then your torque will be 0. Then induction, single phase induction motor cannot start, cannot rotate. So that is the reason the coil is designed accordingly. The auxiliary winding pattern design is different than the main winding. One is thicker, other one is thinner, just to allow difference in resistances so that they cause the alpha. See, if the both, everybody see, if the both auxiliary and main winding either both thinner, the same, their length same, and then either or both are the thicker and they have the same length, then there will not be any angle difference. They will have the same phase difference with respect to voltage, the same amount of the lagging angle. Do you understand? If the both coil are the same pattern, exactly the same size, both are the thicker or both are the thinner, they have same length, then there would not be phase difference between Ia and Im. That's why the auxiliary winding construction is different than the main winding, just to produce some alpha. Because according to this equation, you must have some value of alpha. If it is 0 degree, then your starting torque is 0. Then again, it does not make sense to put the auxiliary winding if it would have the same construction and if it is the same coil. So everybody, do you understand? So I would recommend you, everybody, please write down this equation. This equation will be needed to solve numerical problem. This one, please write torque equal to K, which is called the torque constant, Ia, auxiliary winding current, Im is the main winding current, multiplied by sine of alpha. And alpha is the angle between Ia and Im. So everybody, please write down this equation. The torque equal to K Ia Im sine alpha. Have you all written down that T equal to Ki Im sine alpha?
Yeah, sure have.
Okay, great. Yeah. So now again, and you understood this thing. Now I am taking you to that slide again. So now everybody see, this is the thing I was discussing. Now we just look that torque equation. I mean, I think I was trying to explain that how I can get this value, why I am getting this amount at the 0 moment. That's why I take you to that board. So that is the explanation. Because auxiliary winding and main winding is causing some angle alpha, there is difference in angle. And that angle is causing to produce the torque. Because just we look torque equal to KIAIM multiplied by sine of alpha. That is allowing some value at the zero moment, some starting torque. And that starting torque will start that rotor rotate. And once it will gain 75% of the synchronous speed here at this point, and then you open the switch. You don't need this one. So then only the main winding is working. That is the meaning. So now, as I said that I mentioned earlier today that a ceiling fan is a best example of a single phase induction motor. And also I said that the ceiling fan has the capacitor together with the auxiliary winding. But I cannot see the capacitor here. And that capacitor is needed to improve the power factor. So this means that when I was plotting this on that voltage versus IA and IM, and then those are the lagging angle, if you put the capacitor here, then definitely that will be the leading angle. And that leading angle is much preferred than having the lagging angle, because you all know that leading angle has some benefit. It will improve the power factor. Voltage regulation will be better. System will be much more efficient. That's why in the ceiling fan there is a capacitor. And if you put the capacitor, accordingly the motor name changes, like single phase capacitor start or capacitor run motor. Accordingly it is called. Therefore, based on the arrangement, like this is on arrangement. This is called, you see, split phase induction motor. Split phase. Split phase means it is creating that phase. It is splitting the phase. It is dividing the phase. Accordingly, it is called the split phase motor. But when there will be a capacitor here, then it will have different name. And then I am showing you the all picture. And then in some cases, you don't have centrifugal switch. There is a capacitor and that is permanently closed. So it depends on the application. This means that this split phase induction motor, this configuration is used for some other application, not for the ceiling fan that I am talking. When there will be capacitor for ceiling fan, for example, and then when it will be switch is always closed, other application, even you can see there are two capacitor here connected in parallel, one with the switch. That is for different application. Therefore, depending on different application, there are different configuration. So therefore, so far, I mean, including this on split phase induction motor, single phase induction motor are typically 4 types. So everybody see, one is called split phase type of induction motor, other is called the capacitor start motor, third category is called capacitor run motor, fourth category is called capacitor start, capacitor run motor. So therefore, depending on the applications, there are 4 types. For example, I think here I have written some application. Split phase motor that we just discussed, it is used in blowers, saws, in some pumps. Then capacitor start motor in compressor, air conditioner, large washing machine. You know that because large washing machine should have very high starting torque. Large washing machine. So that's why to gain the high starting torque, you need the capacitor start motor, because that will increase the starting torque much higher. I am showing you the picture. It depends on the application. And then capacitor run motor. We want that the ceiling fan is running smoothly without creating any noise or any sound. We want smooth performance. We want better power factor. We want better efficiency. We want better voltage regulation. To gain all of those capabilities, characteristics, it is called capacitor run motor, meaning that in the auxiliary winding, there is a capacitor and that is also running always. In this case, you don't need any centrifugal switch. Always there will be capacitor in the circuit. And then you see, I have written the example fan or ceiling fan, refrigerator. You know that refrigerator needs very good performance. Otherwise, your food and drinks, everything will not be cold. So that's why to keep those things in good mode, in good shape, you need a capacitor run motor there. But of course, that is the single phase induction motor. So single phase capacitor run type of induction motor. And then again, there are other types of ceiling fan, which has two types of capacitor. Sometimes in some of your house, if you open the ceiling fan, the stator circuit, you might see that there are two capacitors. One capacitor is just for starting purpose and other capacitor is for running purpose. So you might see the presence of two capacitors there in case of the ceiling fan also. But I mean, there are two types, only one capacitor run and then capacitor start capacitor run. Therefore, definitely it is somewhat costly than this one because of the having one more capacitor, but definitely its performance is better. I mean, it is much more smoother, much more quieter in operation. So now you see whatever these classifications and then their applications are, I think so far I showed you that one, that is split phase motor, that picture I was showing you. So therefore everybody see, when it is split phase motor, just two winding, main winding and auxiliary winding. Of course, with that property, this is the property in terms of higher resistance or lower resistance. But then at least there is no capacitor. Everybody keep in mind. Then now the next category here, you see, I am putting capacitor. This means capacitor start motor. So as I said, the example is large washing machine, compressor, air conditioner, which requires the large starting torque. You see, can you see the starting torque amount? This is more than 300%. It is causing the very high starting torque because large washing machine requires very high starting torque. So that is creating, and then again, the principle is the same. Once it will gain about 75% of the rated speed, synchronous speed, then take the auxiliary winding out. So then this is the main winding only. So therefore, there is capacitor together with the auxiliary winding, and that is causing the higher starting torque. Because you see, if you again draw the vector diagram, this voltage versus the current, then you can see. You see, everybody, this is voltage, and then because there is capacitor here, therefore definitely I now it has been leading with respect to the voltage. You see, in the previous picture, IA was downward, it was lagging because it has only the resistance and inductance, but now it has capacitor. So that is causing the leading power factor. IM is as it is. IM is always lagging. Now you see the angle is much more higher. Like it looks like almost 90 degree. So because in the torque equation T K I am sine alpha, if you can make alpha 90 degree, that is the best situation. That will provide you the best torque, maximum torque. So that's why it is representing on a. This means you have to design capacitor such a way, you have to choose a value such a way that will make this situation. That's why you are looking at the very high starting torque. So it just depends on the application. So accordingly, you will be calling this one, as I said, capacitor start motor, capacitor start motor. So therefore, in the exam, midterm exam or final exam, if you are asked, okay, draw the brief schematic of split phase motor or capacitor start, capacitor run, accordingly, you will be showing this picture. Or I said, okay, draw the torque speed characteristics, accordingly, you will be plotting this one or the other one. Then the third category, everybody see, you see, it is called the capacitor run induction motor. In this case, you see there is no switch. So that is the example of the ceiling fan. Therefore, now if you open your ceiling fan today at your home, exactly you will be noticing this circuit. You have one winding, you have the other winding, and there is a capacitor. And then many cases, capacitor got burnt out and then the ceiling fan got stopped. Like your ceiling fan is not running because it got like disconnected. So you see, if this is broken or this got damaged, meaning that the it is not working. Auxiliary winding path is not working. And then at the beginning of the class today, we learned that single phase induction motor is not self-starting. Only one coil is not enough. Ultimately, there is no torque and your ceiling fan got stopped. So in most cases, the issue is with this path. It happens, the capacitor is. But then this, as I told you, this capacitor is needed for the better operation because it is 24-hour in the circuit, always in the circuit. There is no switch because ceiling fan needs that to provide much better operation with improved power factor. And then the other category, as I was telling you, you look its name capacitor restart, capacitor run motor. There are other types of ceiling fan, but there you look there are two capacitor in the with the auxiliary winding. One is called C run. This means this is permanently connected. Other with that switch, C start. So this capacitor is just for restarting time, and then this capacitor always. This means that this on once the speed will be about 75%, then you take it out and then keep this on. So this is the much more improved version. So therefore, on you keep always to have to run it with improved power factor, and at the beginning you will start with the one that will provide your very good and high starting torque. So that is the other structure. So accordingly, you all will remember these four types. That single phase induction motor is split phase type, capacitor restart type, capacitor run type, capacitor restart, capacitor run. I mean, by the name, you can see why it is called. One capacitor for starting purpose and other capacitor for running purpose. Accordingly, the name goes capacitor restart, capacitor run motor. Okay, so then now, so I have two numerical problem for you that you all will be doing. Everybody, is this fine so far? Could you follow me?
Yes, so far, yes.
Okay, great. Now, everybody, please read these two numerical problems. First one, a on by 4th horsepower. You see that the very first thing, it is written on by 4th horsepower. So at the beginning, I told you that all the motor that we are looking, just now I showed split phase, capacitor run, capacitor restart, whatever, always the rating is below 746 watt, always below 1 horsepower. That's why in this problem, it says on by 4th horsepower. This means it is not full horsepower, on by 4th horsepower. That's why these are called the fractional horsepower motor. In single phase 120 volt 60 Hz 2-pole induction motor has a rotary speed of 3420 rpm. Calculate the slip values due to forward and backward rotating field. Do you see? It is asking about what is the value of slip due to forward field and due to backward field for both type of fields. So everybody, and now you solve it. Each of you have calculator, each of you take pen and paper and calculate the value of slip due to forward field and calculate the value of slip due to backward field. So forward slip, you all know that slip equation that you have learned so far in case of three-phase induction motor, and today we discussed. But the backward field slip is 2 minus SFD, means 2 minus forward field slip. And then let me know what is the values you are getting. Everybody, please solve this one. Then let me know that what slip values you are getting due to forward field and what slip values you are getting due to backward field. Has anybody got the result for slip due to forward field?
I got 0.05, I think.
Yeah, that is the forward slip. Yes, the slip, that's right. Yeah. So forward slip is subscriptive. It will be 0.05. That's right. And what is the backward slip?
2 minus that would be 1.95,
Yeah,
right?
yeah, right. 2 minus SF, so it will be 2 minus 0.0, so it will be 1.95. That is will be the value of the slip for backward field. Is everybody getting the same result?
Yes, I just got the same.
Okay. Yeah, you see here, I think everybody see it I was doing here. First I wrote forward slip equation. That is the traditional equation that you already know. Ns minus nr over ns. And then right side I calculated the synchronous speed, 120 f over v. So 3600 rpm. And nr value was given in the problem 3420. So I got 0.05, and then the backward slip SB 2 minus that forward slip. So 1.95. So everybody see this will be the calculation. This is not difficult problem. This is just the slip calculation. The only difference between three-phase induction motor, you just ended up with calculating one slip. Today you are calculating the other slip, and that's why I said that single-phase induction motor theory is complicated than the three-phase. Pretty interesting. Three-phase induction motor should be complicated than the single phase, but the opposite is true. And that is the reason, if you see any electric machine book, always single-phase induction motor chapter is placed later than the three-phase. So same thing I'm noticing when I was the student, long back, undergrad student like you. Always that was my question, that why that single phase induction motor chapter is placed later than the three phase. I think these are the reason, and still I am noticing these days there are lots of the new books by many authors. They all place the single phase induction motor because of this reason, that this is somewhat complicated in theory. Because of the forward field, backward field, you need the auxiliary winding, those capacitors thing are coming. But you remember when we are discussing three-phase induction motor, we did not face those problems. Because it was the three-phase, it created the rotating magnetic field. So there was no lack of magnetic field speed. So that is the difference. Okay, so then now everybody read, you have the another problem. Please read problem number 2. Everybody read number 2. A single split phase induction motor. So therefore you guess which one, the first type that I discussed today. A single split phase type induction motor has an auxiliary and main winding current values of 10 ampere and 15 amps respectively. The auxiliary winding current leads the main winding current by 45 degrees. Then calculate the starting torque of the motor. Consider or assume a torque constant value of 0.6. So everybody see, then which equation to use? It is asking calculate the starting torque. That torque equation, T equal to K Ia multiplied by Im multiplied by sine alpha. Everybody, could you follow me what I said? Did you all write down that equation, torque equation, starting torque T equal to K Ia Im sine alpha, that equation?
Yeah,
That
I've got it.
Yeah, that is showing on the board. Yeah. So if you use that equation, you see torque constant K value is 0.6. And you can see the value of current. IA value is 10 ampere. IM value, main winding current 15 ampere. And what is the alpha? Alpha is that 45 degree. You see, the auxiliary winding current leads the main winding current by 45 degrees. So that is the value of alpha. Therefore, this alpha is that split phase type that I was discussing, this one, this alpha. And you see, really the auxiliary winding current is leading IM by alpha. So in the alpha is that 45 degree in the problem that we are discussing. That is the alpha value. So then calculate the torque value. So therefore, once again, T equal to K IA multiplied by IM multiplied by sine of alpha. So then, have you got the result? Anybody? The result you express in Newton meter.
$63.6.
Yes, looks like correct. So everybody see here, I have done that. I mean, it's just a one line problem. Is number 2T, KIA IM sine alpha. Everybody please look this one and then substitute the values. So you are right, 63.6 for Newton meter. K value is 0.6. Everybody look. Armature, sorry, the auxiliary winding current value is 10 ampere. IM is 15, and then sine alpha. Alpha is that 45 degree. So just keep in mind, instead of saying in the problem the alpha value is 45 degree, it says in that format that the auxiliary winding current leads the main winding current by 45 degree, meaning that that is your alpha. So you took in that way the definition of alpha. Alpha is the angle between auxiliary winding current and main winding current. And then it says that is leading because definitely it is a split phase type and definitely auxiliary winding current will lead. In fact, always for any type of motor, always auxiliary winding current will lead the main winding current, whatever the amount of angle is. That's the thing. So that's why everybody see you are getting that 63.64 Newton meter. Is everybody fine?
Yeah, I think we're good.
Everybody, are you calculating? Are you?
Yeah, that's what I got.
Okay. Everybody, please make practice. Then it will be good practice for you because next week you will have the midterm exam 2 on coming Thursday, October 22. Okay, so therefore, I think I already have uploaded this updated slide on eCoursera. I already did. So you can see there these calculations, this slide. Now moving forward, I think today we don't have time, only few minutes I can talk, 2 to 3 minutes. Now, I mean, starting from now on the next class, so I'll be discussing that universal motor and permanent magnet DC motor, and then followed by other type of motors. So as I said, that universal motor, as you can see by the name universal, the name goes because it operates on both AC and DC. This means that if you apply the AC, it will work. If you apply the DC, the same motor will work. And as I said, everybody notice, those are called the series motors. So just we are looking the series DC motor until that previous class you looked. This means it has the series winding in addition to the main winding. So therefore, everybody keep in mind that basically universal motor is the series motor. Just you are applying AC or the DC. So, but easily you can guess, everybody you can guess that of course there is some difference between the application of AC and DC. Different, for sure, that motor will behave differently. You will not get the same type of response, same type of output by the DC and the AC. So, and then I have ahead of time, I have written something here for you. Under AC excitation means when you are powering the motor by AC, the universal motor produces lower speed, poor power factor, and pulsating torque as compared to the DC excitation, meaning that the DC application. So we will be discussing these things extensively in the next class. I will take you to the board, and then again there is so numerical problem. So today I will not discuss. We'll run out of time. So everybody see the easily you can guess. So you can think about this on this bullet ahead of time. Why is this conclusion? So this looks like that DC application is better than the AC application to the universal motor. It looks like, because I clearly said that the difference between AC application and DC application to the motor, the universal motor will produce lower speed. This means if it is DC, then higher speed. Power factor is poor. Easily you can guess this point why it is poor power factor, because DC is not related to power factor. Because if you apply the DC, then if there is capacitor in the circuit, then that will be open circuit. If there is inductor in the circuit, that will be short circuit. So that is eliminating the concept of power factor. Power factor is always 1, right? So in case of the DC. So that's why easily you can guess that if you apply the AC to the same motor, to the same series motor, then because it is AC, it has the frequency, then there is the question of inductance and capacitance. There will be inductive reactance, capacitive reactance. Resistance is fine. So that's why the question of power factor is coming. And then pulsating torque, easily you can guess when you are applying DC, DC is constant. It is not time varying. But once you are applying the AC, it is varying with respect to time. That is the reason it will cause the pulsating torque. And then I will explain in the next class that how you are getting the low speed. So it looks like the motor will work on both system, on both power source, but there is difference in terms of their performances. So we'll be discussing, and then these are the application. Electric shavers, sewing machines, hair dryers, drills, grinders, vacuum cleaners, etc. These are the application. So okay, so with that, let's conclude it. I think some of you have next class. So I will continue this on. We will discuss, and then also I will talk about the permanent magnet motor in the next class. So does anybody have any question? Anything?
No, I don't. I think I'm good so far.
Okay. Thanks.
Professor, I have a question.